Welcome everyone to the deep dive. All right, today we're jumping into something pretty fundamental in AI right now. The scaling problem with large language models, LLMs. The scale transformers, they get powerful, sure, but compute and memory, they just skyrocket, right? Through the roof. Existing tricks, well, you could either share parameters or adapt the compute, but never really both at the same time. Then comes this new idea, Mixture-of-Recursions or more. It's like a recursive transformer, but with a twist. You reuse a shared stack of layers across recursions. Parameter efficiency, check. You add these lightweight routers. They assign different recursion depths to each token. Adaptive thinking per token, check. You focus quadratic attention only on the active tokens. Memory access, way more efficient. You design KV caching, that's recursion-wise, store only what's needed, skip the rest. You even try KV sharing from the first recursion. And prefill latency just plummets. So you train models from, say, 135 million up to 1.7 billion parameters. Same FLOP, smaller size. Validation perplexity, lower. Few shot accuracy, higher. Inference throughput, whoosh, up to 2.18 times faster. And you realize,
It's not just parameter sharing, and it's not just adaptive compute, it's both, Together, in one framework, people might say, but recursive models lose quality. You show them the Pareto frontier more R beats vanilla, beats the old recursive models. They say, but efficiency sacrifices power. Your model matches big model quality, but skips the big model cost. And you realize you didn't just make a faster transformer, you made a transformer that actually knows when to think hard and when to kind of rest. That sounds like the future. So yeah, that's the core idea we're exploring. These models are amazing, but wow, do they eat resources? We're constantly trying to make them smarter, faster, more efficient.
Oh, absolutely. It's kind of comical if you step back. Imagine, right, the LLM is this absolute stunning, unbelievably fast hypercar. I mean, it's brilliant, powerful, does things we only dreamed of a few years ago.
Right.
But here's the catch. We're trying to park this hypercar in a garage, frankly, that was built for a bicycle. The compute, the memory demands, they're just astronomical. It feels like the whole system could just, crush under the weight of its own brilliance.
Oh, yeah, I can see that.
And for the longest time as researchers, we were stuck in this really frustrating, either a situation you could try to make the car physically smaller, that's parameter efficiency, right? Shrink the model size.
Okay.
Or you could try to make it only drive flat out when absolutely necessary. That's adaptive computation.
Yeah.
Make it think only when it needs to think hard. But getting both at the same time, it just wasn't happening. It's a real head scratcher. Always this trade-off. And then, boom, the breakthrough. Mixture-of-Recursions, more. It's really this unified framework, the first one, that finally manages to bring these two critical efficiency axes together. Think of it like designing a hypercar that can magically shrink down to bicycle size when it needs to, and it intelligently figures out exactly how much fuel it needs for every single little trip.
Okay, that's a great analogy. So how does it actually do that?
Right, so a few key things. First, more reuses a shared stack of layers across its recursion steps. That's the parameter efficiency bit.
Oh.
It's like having one truly brilliant, super multi-talented core team in your company that can just handle all the different stages of a complex project instead of, hiring a brand new specialist for every single little task. Saves a ton of overhead.
Got it, the shared team.
Check. Then it adds these really clever lightweight routers. And what these do is dynamically assign different recursion depths to each token. Basically, deciding how many times each little piece of information needs to be processed or thought about.
So different amounts of thinking for different words.
Exactly. Adaptive thinking per token. Check. It's almost like if your brain knew precisely how much mental energy a particular thought needed, From just a quick glance to a full-on philosophical deep dive, saves energy on the easy stuff.
Makes sense.
And finally, the way More handles attention and caching. Its quadratic attention only focuses on the active tokens at each step. And its key value caching, the KV caching, is, recursion-wise, super efficient.
The librarian analogy from the intro.
Yeah, exactly. Like a really meticulous librarian who only keeps the research papers you're actively working on right now on your desk and instantly puts everything else back in the archives. Way more efficient memory access. Check.
Okay.
So the real kicker, the big reveal here, is that More isn't just one of these tricks in isolation. It's not just parameter sharing. It's not just adaptive compute. It's both, right? Working together seamlessly in one kind of elegant framework.
Right, the unified part.
Yeah. It's about building a transformer that genuinely knows when to think hard and when it can afford to rest.
Yeah.
And that feels like the future of efficient AI, doesn't it?
It really does. That's a fantastic overview, framing a super complex problem and This elegant solution. You've definitely got my interest piqued. So now that we have the high-level picture, let's dig in a bit. Let's unpack the specific mechanisms. You mentioned parameter efficiency, reusing that shared stack of layers. How exactly does Moore pull that off? And how does that help with things like fully sharded data parallel, FSBP, which people use for training huge models?
Right, great question. It really boils down to this technique called layer tying, which is kind of central to recursive transformers in general. So in a standard transformer, every single layer has its own unique set of parameters.
Yeah.
Billions of them for big models. It adds up fast. More, and recursive models, they take a fixed number of recursion blocks. Think of these as the core processing units, and they repeatedly apply the same shared pool of parameters multiple times. So you dramatically increase the model's effective depth, how many processing steps it goes through, without actually increasing the number of parameters you need to store or train.
Okay, so depth without the parameter cost.
Exactly, and that amortization of the memory footprint during training is just huge. And yeah, for techniques like FSDT, FSDP works by splitting, or sharding, the model's parameters across many GPUs so you can actually fit these massive models into memory.
Right.
Well, if you're constantly reusing the same set of gathered parameters across all your recursive steps, FSDP becomes incredibly efficient. You're not constantly having to fetch entirely new, massive sets of parameters from all the other GPUs for every single step. You fetch them once for the shared block and reuse. It cuts down communication overhead massively.
That makes a lot of sense. Less shuffling data around.
Precisely. And the research found that a particular strategy called middle cycle sharing seems to work best. What this means is the very first layer and the very last layer, they get their own unique, dedicated parameters.
Okay, special entry and exit.
Right. Gives the model distinct ways to process the initial input and generate the final output, which often seems crucial. But all those intermediate layers, the ones doing the heavy lifting in the middle, they cyclically reuse that same shared set of parameters. It's a nice balanced specialized ends, but massive parameter savings in the core processing. Kind of the best of both worlds.
So it's like having this single, really highly efficient brain module that gets applied over and over again through the processing pipeline, makes the whole thing super compact without sacrificing that processing depth. Clever. Okay, let's pivot to the second big innovation, adaptive computation. You said Moore enables adaptive token-level thinking, different amounts of computation based on complexity. This is where those lightweight routers come in. How do they actually work? How do they decide, how deep a token needs to go?
Exactly. This is the intelligent gatekeeper part. These lightweight routers are the key. They dynamically decide for each individual token how many recursion steps it actually needs. We looked into two main ways of doing this routing: expert choice and token choice.
Okay, expert choice first.
Right. With expert choice routing, you can think of each recursion depth, like step 1, step 2, step 3, as being an expert. And at each step, that expert selectively chooses a top K subset of the tokens to continue processing into the next step.
So only some tokens get promoted to the next level of thinking.
Pretty much. Only the tokens the router deems most complex or important at that stage get to go deeper. The big advantage here is it guarantees a static compute budget. You know exactly how much work is happening at each step, and it gives you perfect load balancing across your hardware, because each expert explicitly picks a fixed number K of tokens.
Sounds neat. Any catches?
Well, one potential issue during training is something called causality violation. The router might sort of inadvertently peek ahead at future tokens when making its decision, which obviously you can't do during real-time inference when you're generating text one word at a time.
Cheating, basically.
Kind of. So to prevent that, we use what's called an auxiliary loss, specifically on the main router. A loss function in machine learning, it tells the model how wrong it is. An auxiliary loss is like an extra little penalty or guide signal that specifically trains the router to make good, reliable decisions without peeking ahead. And interestingly, a simple linear router with a sigmoid activation function turned out to be really effective for this.
Okay, so auxiliary loss keeps the router honest during training. What about the other one, token choice?
So token choice routing is different. Here, each token makes a single decision right at the beginning about its entire recursion path. Like, okay, I'm going 3 steps deep, and that's it.
One decision up front.
Yep. The good thing is, there's no peeking ahead involved at all, so it inherently avoids that causality violation problem.
Sure.
But the potential downside is load imbalance. You might end up with, say, way too many tokens deciding to go 5 steps deep and hardly any choosing 2 steps. That means some of your recursion depth experts or processing units could be overloaded while others are sitting idle.
Right, uneven workload.
Exactly. So to handle that, you apply a balancing loss. Another training signal, basically, that encourages the tokens to distribute themselves more uniformly across the different possible recursion paths.
Okay, two different ways to manage the flow. Seems like expert choice, maybe with that auxiliary loss fix, might be a bit more controlled, but how does the router, in either case, actually learn which tokens need more thinking? What makes a token complex in its size?
This is where it gets really cool, I think. This is where you see Moore's adaptive intelligence really shine. The router essentially learns to assign recursion depth based on the semantic importance of the tokens.
Semantic importance, like the meaning.
Yeah. For instance, content-rich words, nouns, verbs, important adjectives, things like people, drugs, or even a phrase like offensively confident. These tokens tend to get routed through more recursion steps. They receive that deeper, more intensive processing, that extra thinking.
While the simpler words?
Exactly. Meanwhile, function words and, the GEA, punctuation like a hyphen, or even just a new line character, words that carry less core meaning. They tend to exit the recursion much earlier. They just don't need as much processing to figure out their role.
Wow.
It beautifully illustrates the model's ability to focus its limited computational resources precisely where they'll have the most impact, like a really smart editor who knows exactly which sentences need the most polish and which are fine as they are.
That's incredibly intuitive.
Yeah.
And efficient. Okay, let's shift gears slightly to another really critical bottleneck, especially for inference, the key value cache, the KV cache. For listeners maybe not super deep in transformer guts, could you give us a quick refresher on what KV pairs are and why caching them becomes such a headache, especially with long texts?
Absolutely. So inside a transformer, when it's processing text for every word or token, it generates these special representations called key and value pairs. You can think of them as highly compressed summaries of that token's information and its context up to that point.
Okay, summaries.
Yeah. And these summaries are absolutely crucial for the attention mechanism. That's the part that lets the model figure out how different words in a sentence relate to each other, even if they're far apart. Now, to generate the next word, the model needs to look back at the keys and values of all the preceding words.
Right, the context.
Exactly. So instead of recalculating these KVs every single time, we cache them. We store them in memory. This is KV caching. The problem is, especially when you're dealing with long sequences of text, maybe summarizing a long document or having a long conversation, this cache of keys and values just grows and grows and grows. It can become enormous, often consuming more memory than the model parameters themselves. This huge memory footprint is a major bottleneck, limiting how long a context you can handle and how fast you can generate text.
Gotcha. Big memory hog for long contexts. So how does Moore tackle this?
Moore brings in two specific tailored KV caching strategies to really optimize this. The first one is called recursion-wise KV caching.
Okay.
With this approach, the key value pairs are selectively stored only for the tokens that are actually routed to participate in a given recursion step. So if a token exits early, its KVs aren't kept for the deeper steps. And the attention calculation within a specific recursive layer is restricted only to those locally cached KVs from tokens active at that depth.
So you only keep the KVs for the tokens currently in the room, so to speak.
Precisely. This promotes what we call block local computation. It drastically reduces the total size of the KV cache you need to store, which is great for memory efficiency. And it also lowers the input-output demands on the GPU memory bandwidth because you're accessing smaller chunks of data. This strategy is generally preferred when you need maximum precision, as it ensures tokens always attend to the most relevant, up-to-date context available at their specific processing depth.
Makes sense. Very targeted. What's the second strategy?
The second one is recursive KV sharing. This one is quite different. Here, the key value pairs that are computed during the very first recursion step are just reused. They get shared across all the subsequent recursion steps for all tokens, regardless of whether they exited early or not.
Whoa, okay. Reuse the first step's homework for all future steps.
Kind of. The primary benefit here is maximal memory savings. You only compute and store that initial set of KVs, and it leads to significant speedups, especially for what's called prefill operations.
Prefill latency, that's processing the initial prompt right before generation starts.
Exactly. When you feed the model your initial prompt at your question or the beginning of a story, it has to process all of that text at once to build the initial context. That's the prefill stage. Recursive KV sharing makes this much faster, because you don't need to recompute those initial KVs over and over again for the deeper potential recursive steps during that phase.
Okay, so let's revisit the librarian analogy. Recursion-wise caching is like the super organized librarian pulling only the exact books for your current research phase. Recursive KV sharing sounds like the librarian gives you all the potentially relevant background material right at the start, and you just keep referring back to that original stack, even when you're deep into Chapter 5 revisions. What's the trade-off there? Is the shared stuff always good enough?
That's a perfect way to put it. The trade-off is exactly that. A balance between maximum memory efficiency and potential hits to performance accuracy. Recursive KV sharing, as you said, offers the biggest memory savings and can dramatically speed up prefill. That's its big win. But because you're always reusing those KVs in the very first initial step, it can sometimes lead to a slight dip in performance quality, especially when you're using the expert choice routing strategy.
Why expert choice specifically?
Because expert choice routing is usually quite precise. Tokens get routed deeper because they need more refined processing. If they get routed deeper, but are still forced to attend to the same potentially stale or less refined KV context from the very first step, there can be a mismatch. The context they're looking at hasn't evolved with their own deeper processing.
Okay. The context doesn't keep up with the thought process.
Kind of, yeah. Interestingly, though, for the token choice routing strategy, remember, where tokens make that single upfront decision, recursive KV sharing can actually sometimes help performance.
Really?
Well, in that scenario, the initial routing decision might be a bit less precise. So having that broader shared contextual information available from the first step's KVs, even if it's not perfectly tailored, can sometimes compensate. It gives the model more background information to work with across all its steps, potentially making up for a routing choice that wasn't perfectly optimal. So it's a nuanced choice, right? Depends heavily on your routing mechanism and whether your priority is absolute maximum memory saving or ensuring the most precise context at every single step.
Fascinating. Really highlights the intricate design choices involved. Okay, we've had a really thorough look at the shared layers, the clever routers, the smart caching. But, the proof is in the pudding. All these cool ideas need to actually translate into measurable wins. Can you walk us through the empirical results? How does more actually perform in practice?
Absolutely. And the results are pretty compelling, I have to say. Let's look at it a few ways. First, what happens if you give more models and standard vanilla transformer models the exact same training compute budget? Meaning they perform the same total number of calculations, the same FLOPs during training.
Okay, fair fight on compute.
Right. In that scenario, more models, for instance, an expert choice variant with 2 recursion steps consistently achieved lower validation loss or perplexity. Remember, lower is better, means the model understands language better. And they achieved higher few-shot accuracy, better at learning new tasks quickly.
Better performance with the same compute.
Yes. And here's the kicker. This was despite the more models using nearly 50% fewer parameters than the vanilla baselines.
Wait, half the size, but better results with the same training compute. How does that work?
It's actually straightforward when you think about it. Because more is so much more efficient per step due to parameter sharing and adaptive compute, within that same fixed FLOPs budget, it can actually process more training tokens. It sees more data, gets more learning done within the same computational cost, and that translates directly to better final performance.
Okay. More learning bang for your compute buck.
Exactly. Well, you also look at it the other way. What if you train on the same amount of data? Here, the more models naturally consumed less compute overall. We saw significantly reduced training times, like 19% faster and about a 25% reduction in the peak memory needed during training. So it's just fundamentally a more compute-efficient architecture.
Faster training, less memory. Sounds good. What about scalability? Does this advantage hold up as models get bigger?
Yes, scalability looks really promising. Using something called an isoplop analysis, which basically lets you compare models fairly across different sizes and compute budgets, more consistently outperformed other recursive baselines. And importantly, it matched or even exceeded the performance of standard vanilla transformers for models larger than about 360 million parameters, scaling well up to the 1.7 billion parameter models tested.
So it's not just a trick for small models, it scales up effectively.
Correct. It really seems to push the Pareto frontier. You're getting better quality and lower computational cost, which is kind of the holy grail in model efficiency research, isn't it?
It absolutely is. Better quality, lower cost. You can't argue with that. That's incredibly impressive for training. But what about, the real world? Deployment. How does more perform when it comes to inference throughput, getting answers back to users quickly?
Yeah, inference throughput is critical for actually using these models. And this is another area where more really shines. The results show up to a 2.18 times faster inference throughput compared to both vanilla transformers and existing recursive baselines.
Whoa. Okay, more than double the speed in some cases. That's a massive difference for deployment. What's driving that huge speed up? Is it just the fewer parameters?
It's actually a combination of factors, primarily two powerful mechanisms enabled by Moore's design. First, because it's a parameter-shared architecture, it can effectively use a technique called continuous depth-wise batching.
Continuous depth-wise batching. Sounds technical.
It basically means you can keep the GPUs incredibly busy, maintaining really high utilization. As some tokens finish their required recursion steps and exit the process, the system can dynamically fill those now vacant slots in the processing batch with new incoming tokens immediately. It avoids those wasteful bubbles or idle periods you sometimes get in complex pipelines.
Ah, keeping the assembly line constantly full.
Exactly. And second, there's Moore's early exiting mechanism itself. Thanks to the dynamic routing, tokens that the model deems simpler to process finish their computation and just leave the pipeline earlier. This directly frees up computational resources, tensor cores, memory bandwidth, allowing more tokens overall to be processed within the same amount of time. It boosts the overall throughput significantly.
Okay, so it's both keeping the hardware busy and letting simpler tasks finish faster to make room for more work. Very efficient flow. It sounds like this adaptive depth thing in Morka isn't just about raw speed and efficiency, though. It feels like it connects to how the model actually thinks. This brings up that really interesting idea of latent reasoning, the internal processing the model does without necessarily writing it all out explicitly. How does Moore's architecture fit into that?
That's a really insightful connection. And yes, this is a profound aspect of Moore. Its dynamic routing mechanism directly enables this kind of latent thinking or deeper processing during the actual decoding of each token. This is quite different from some other approaches you might see, where maybe the model generates explicit chain-of-thought steps first, or uses special pause tokens to deliberate before generating the final text.
So Moore integrates the thinking into the generation process itself.
Exactly. It's happening implicitly, token by token, guided by the router. And our qualitative analysis really backs this up. We see a clear correlation. The recursion depth that the router chooses for a token directly reflects its perceived semantic importance or complexity.
Like we talked about, content words go deeper.
Right, those content-rich words, the key concepts, they get more recursion steps, essentially. A deeper, more refined internal thought process. The less critical function words exit earlier. It strongly suggests the model knows, on some level, where to allocate its deeper computational resources.
And that leads to better quality, potentially.
Yes, and what's really powerful about this is it enables something called test time scaling. Because the depth is dynamic, you can actually choose to increase the maximum allowed recursion steps during inference when you're using the model.
You can tell it to think harder on the fly.
Pretty much. You give it a bigger budget for recursion depth at test time, and often the generation quality actually improves. It's like giving the model permission to think harder when needed, and this translates directly into better performance. It offers this really neat new control knob for trading off a bit more compute at inference time for potentially higher quality output.
Wow. Okay, so Moore isn't just efficient, it's enabling a more intelligent, adaptive kind of internal reasoning that you can even tune after training. That feels incredibly compelling. As we kind of start to wrap up this deep dive, what are the really big takeaways here? What are the profound implications of Moore, and where does this research go next? What's the road ahead for this kind of technology?
I think the implications are truly significant. Moore provides a concrete blueprint for building these incredibly powerful large language models in a way that's simultaneously high-performing and remarkably resource-efficient. That's huge for making cutting-edge AI more accessible, right? More usable across a wider range of applications by more people and organizations.
Democratizing AI power in a way.
In a way, yes. Looking ahead, there are several really exciting avenues for future research. One big one is reasoning more models. Can we train the router not just on semantic importance, but specifically to adapt to the necessity of complex reasoning steps, like chain of thought? Imagine a model that doesn't just blindly follow a reasoning chain, but intelligently decides how much internal thought or how many steps are truly needed for this specific problem to get an accurate and efficient answer.
Smarter reasoning on demand.
Exactly. Then, obviously, there's further scaling. The current work goes up to 1.7 billion parameters. The natural next step is pushing this much further training. More models at, say, 3 billion, 7 billion parameters, and beyond. And exploring techniques like continued pre-training, where you take an existing large LLM checkpoint and adapt it into an Empirical architecture, could significantly cut down the immense costs of training these giants from scratch.
Building on existing work. Makes sense.
We also need to look at adaptive capacity control. Right now, especially with expert choice routing being so precise, it's a bit hard to flexibly adjust after training exactly how many tokens get routed deeper, that K-value. Developing ways to make that capacity more dynamically adjustable at inference time would be really valuable.
More knobs to turn.
Right. And critically, exploring compatibility with sparse algorithms. Combining Moore's token-level adaptive recursion with techniques like structured sparsity, which removes less important weights or connections within the layers, could unlock even greater computational savings. Two different kinds of efficiency working together.
Layers of optimization.
Yeah. And finally, a huge area is expansion to multimodal and non-text domains. The core Moore recursion block is pretty much modality agnostic. It doesn't inherently care if it's processing text or image patches or audio features, so applying this adaptive depth mechanism to vision models, speech processing, maybe unified multimodal architectures, that's incredibly promising, especially for things involving long contexts, like processing entire videos or long audio streams, where Moore's memory efficiency and throughput gains could be even more impactful than they are for text.
Wow. So the potential applications really spread far beyond just language. What an absolutely incredible deep dive into Mixture-of-Recursions. It's really elegant, isn't it? How Moore manages to unify these different efficiency approaches, the parameter sharing, the adaptive compute, the smart caching, all into one coherent, powerful framework, and seemingly without sacrificing quality. In fact, often improving it. It genuinely feels like a significant leap forward for making high-performing AI more practical and accessible.
It really does. And it leaves you thinking, right, if we can get this good at making models that know when to think hard and when to rest for language, what new frontiers really open up when we start applying this kind of adaptive intelligence to even more complex, perhaps more ambiguous real-world problems beyond just processing sequences?
That is the question, isn't it? And maybe something for you, the listener, to ponder too. How much more efficient could your own thinking be, right? If you could somehow dynamically allocate your mental energy, only diving really deep when it's truly necessary. Perhaps Moore isn't just a technical blueprint for the future of AI, but maybe even a bit of a metaphor for smarter learning and problem solving for all of us. Well, that's all the time we have for this deep dive. Thank you so much for joining us, and as always, keep that curiosity ignited.